Okay, so now we're going to take a look at using confidence intervals for means. And again, very similar to a confidence interval for a proportion, except now we're looking at quantitative data. So in order to estimate an unknown population parameter, we will start with a statistic that provides a reasonable guess. The chosen statistic is called the point estimate for the parameter. We then will use this point estimate to construct a confidence interval, which uses the sample data to estimate an unknown population parameter with an indication of how precise the estimate is and how confident we are the results are correct. Thus, we have the two components, the interval, which we compute and will denote AB, and then the level of confidence. Are we 90% confident, 92, 95, 99, etc.? These values vary, and in general, we have this picture here, is that our sample statistic will be in the middle of our interval, and theoretically, we should capture the truth, but not always. Remember, this is an estimate, so some of your estimates will capture the truth, some of them will not. And this wiggle room is called the margin of error. Now, keep in mind, X bar is considered low bias or an unbiased estimator if it's randomly sampled. But if we have things like sampling errors such as convenience sampling or voluntary response, or non-sampling errors such as response bias, non-response bias, undercoverage, the confidence interval can't distinguish the bias, it just simply estimates the truth. Now, we have this general formula here, the point estimate plus or minus the critical value, which now we will be using the t star, and we will be getting that from our table here. So this is our z table, and here is our t table. So we'll have to calculate the degrees of freedom, and then depending on the level of confidence, we'll have to find which of these values we'll use. And then our standard error of the statistic, again, we can just pull that from the formula sheet. So we're going to have this form here for quantitative data, and specifically for one sample quantitative data, we will start at the sample mean plus or minus a t star times the standard error of the statistic here. Now, assuming this is from A to B, the way we can find the point estimate if we're just given the interval is to take or find the middle of it. So we'll add the two variables, the two endpoints of the interval, and divide by 2 to find the middle. In order to find the wiggle room, the margin of error, which is this part here, the critical value and the standard error of the statistic, we're going to take, since we're looking for this chunk here, we're going to take the difference between B and A and divide by 2 to find the margin of error. And then this might feel familiar from when we found the sample size for a proportion. So hang in tight, it's going to come back and haunt us. Now, the way we interpret our confidence interval is that we are C% confident, not confidence, that the interval from blank to blank captures the true population mean of blankety blank blank. In repeated sampling of size n, C% of all constructed confidence intervals from this population will capture the true population average of blankety blank blank. So let's go ahead and take an example here. This is pulled from one of the StatsMedics practice tests from last year's modified AP exam. And suppose a park ranger at a large national park wants to estimate the mean diameter of all the aspen trees in the park. The park ranger believes that due to environmental changes, the aspen trees are not growing as large as they were in 1975. The conditions for inference have been met, and the park ranger uses the sample data of 30 trees to construct the following 95% confidence interval. And we have that value from 5.6 to 7 inches. So here's a few questions for you to try out on your own. Find the point estimate and margin of error, interpret the confidence interval, interpret the confidence level, and then based on our confidence interval alone, is it plausible that the diameter of an aspen tree can be 8 inches wide, or an aspen tree. Sorry, y'all, a little late when I was typing these notes. So let's go ahead and take a look at those 4 questions. So go ahead and pause the video now and try and work through this problem here, and then we'll come back together and compare. So go ahead and pause now. Okay, so hopefully your answers look similar to mine, but looking here at the point estimate, we're using the sample mean. And notice here that both my sample mean and my margin of error now have units. When we were working with proportions or categorical data, since it is a proportion of the data, we were typically used to decimals or percentages. While that is totally likely for means, means are looking at quantitative data. So the context of our responses needs to include the context from the questions here. So since we're looking at tree diameter, we have to make sure that our sample mean is in the same units as our sample data. So here I have a point estimate of 6.3 inches plus or minus 0.7, and that's how I obtain the interval of 5.6 to 7 inches. Now, interpreting the confidence interval would sound something like, we are 95% confident that the interval from 5.6 to 7 inches captures the true population average diameter of aspen trees, or your interpretation can look something like mine. Either one is fully acceptable. Again, notice that I include the confidence level, I include context, and I include my interval here. Now, confidence interval is where we think the data happens based on our sample statistics, but now, sorry, let me move that. The confidence level has to deal with our process and procedure. So in repeated sampling of size 30, 95% of constructed 95% confidence intervals would capture the true population average aspen tree diameter. And again, this just deals with sampling variability. Sometimes your sample will capture the truth, sometimes it'll get pretty close, and sometimes it'll completely miss it. We don't make the rules, but we do analyze and evaluate them. So that's an interpretation there. And then lastly, is it plausible that the diameter of an aspen tree can be 8 inches? Since 8 inches is not contained within our 95% confidence interval, it is not a plausible value for the diameter of an aspen tree. Now, this value may still occur by chance alone, however, our confidence interval provides evidence that it might not be highly likely. So again, it is totally possible that 8 inches could be the diameter of an aspen tree. Maybe it's 1 out of a million, who knows? So it is totally possible. Now, based on our confidence interval and the sample mean of 30, or not 30, but our sample mean of 6.3 inches, we might have some evidence that suggests that actually our diameters seem to be a lot less than 8 inches. So while it could happen by chance alone, it's not really as likely. Okay, so let's take a look now at actually working with a one sample t interval for means, and we're still going to use panic. Again, here we're trying to estimate the true population mean of the whatever the context is. Our assumptions remain the same. We need a randomness element, we need the independent condition, and we need to meet normality by one of these 3 criteria. If our conditions are met, we will use a one sample t interval for a mean. We will use the following formula to compute our test statistic with this degree of freedom, and then the interpretation will still be the same. So here, let's take a look at this example. The local ranger station tracked and tagged 2,844 adult female black bears in a national park. A random sample of 19 adult female black bears from those tagged had an average body weight of 203 pounds with standard deviation 25 pounds. It is assumed due to the large sample size that the population of adult female black bears is normally distributed. And then there should have been a follow-up question that says, construct and interpret a 95% confidence interval for the estimate of the typical weight of a female black bear. So here we are, we've got a sample size, we've got what we believe a population size, some more information about the population. We are going to panic. So go ahead and try it for yourself. I'm also going to do it, and then we'll come back together. Okay, so hopefully you were able to try and work along, and if you have a calculator, maybe you did find the interval. But Mr. Pinto, where do I find t star? So when we did a confidence interval for a proportion, we had set critical values because we were using the standardized normal distribution and using the critical values provided by the z-curve. So here, very similar, and I'll go through this now, but the parameter we're trying to estimate here is the true population average weight of a female adult black bear, specifically at this park. Now, in order to conduct this interval, we must ensure the conditions are met. Here, we used a random sample of 19 female black bears. We can assume that 19 female black bears is less than or equal to 10% of all female black bears at this park. And that's true. Our 19 is definitely less than 2,844 of these female black bears. Next up, the normal model is appropriate since, and you have to state which one of the 3 reasons. Here, our sample size would not be large enough, and we also don't have the full data to make the distribution and try and identify any major skew or outliers, but we were told that the population is normally distributed. So here, the normal model is appropriate since the population is normally distributed. Since our conditions are met, we use a one sample t interval for a population mean, and it has this general formula here. Our statistic, which is the sample mean, plus or minus our critical value times the standard error of the statistic. Here we have 203 plus or minus t star times these values here. and I'm going to move my face over now. The degrees of freedom here are n minus 1, and that's essentially saying if I were to line these 19 female black bears up, and bears had the ability to recognize autonomy, 18 of those bears could select where they'd want to go, and the last bear is not able to select where they want to go because their place would be determined. In the same way, for each parameter that we're trying to estimate, that kind of is set because we're trying to estimate this one parameter. So there's this big mumbo-jumbo complication with degrees of freedom, but for now, in our intro-level stats course, let's just go ahead and worry about n minus 1. So here, n minus 1 would be 19 minus 1 is 18. So now what I do is I go to my handy-dandy t table here, and this is going to come after the z table. So here, very similar, we're going to look at our confidence level, which we said 95%, and then these are my degrees of freedom. So z is what happens when we have an infinite amount of degrees of freedom, hence we know the population. But here, we know that there's 18 degrees of freedom. So 18 degrees of freedom at 95% confidence gives us a t-star of 2.101. That is the new critical value. And we see as the degrees of freedom increases, it closely approaches the values that we believe to be true about the standard z-curve. This table's a little wonky, but you can see it only goes up to 30, because after 30, we start using the central limit theorem to use an approximately normal distribution. And then for the rest of these values, you'll just round down. So if you got something like 46, you'll round down to 40. If you had something like 59.6, which we shouldn't, we'd round down to 50. This is what we call a conservative approach. But if you have your handy-dandy calculator and you've already named the test, you don't have to worry too much about explicitly listing t-star, but it is good practice for the multiple choice section. So if I were to replace this with 2.101, or using my calculator command, filling in these values here, I would obtain the following interval, 190.95 to 215.05. Thus, we are 95% confident that the interval from 190.95 pounds to 215.05 pounds captures the true population average weight of a female adult black bear. And what I forgot was for this park specifically. Since we took a random sample here, I can't generalize to Yosemite or any other national or state park. I can only generalize to the female adult black bear population at this park specifically. So that is an example of using a one sample t interval for a population mean. Now you have the following here, and as much as I'd love to go through this process with you, I believe you are fully capable to identify your parameter, check your assumptions, name your test or interval, and type in a few buttons for your confidence interval. But I will give you the answer here to make sure that you can check your work. So it looks like we had a mean of 27.2, a sample standard deviation of 1.8, and a sample size of 10 cars. And we're going to construct a 95% confidence interval. Your interval should be somewhere between, I'll write this in for you, your interval should be somewhere between 25.912 and 28.488 miles per gallon. So that's the easy part there. I'm going to leave the interpretation, the assumptions, and the name all up to you all. And then, of course, in true fashion, we have an applied question here at the bottom, which is just saying, based on our interval, would we conclude that the claim that the new model has an average of 29 miles per gallon? Well, based on our interval, I think you can answer that. So let me know if you have any questions on this, but good luck. And next lesson, we'll talk about some properties of the confidence interval for mu.